All right. Hi, everyone. My name is Alper. I'm the Education Content Manager for this year's CodeDay Labs. I'm happy to welcome again for the third time Dr. Ben Amor, and he will be teaching you guys Intro to Robot Learning and Evolutionary Algorithms in particular. So, Heni, if you'd like to begin.
Absolutely, my pleasure. Thank you so much, Alper. Thank you, everyone, for joining. I was just saying to Alper, it's the summer. I really appreciate you spending time with me instead of being on the at the beach. Yeah, I think in response to that, I'll try to make this lecture as interesting and as fun as possible. By the way, don't hold back. Yesterday, I didn't see too many people raising their hands and asking questions throughout the talk. Feel free to do that. Like, don't worry. Just kind of, if you have something you want to clarify or something to push back on, don't worry. Just kind of challenge me. Okay, so today we'll be talking about evolutionary algorithms, which is one of the coolest topics out there in machine learning, robotics, and all of computer science. It's really fun. And if you take anything from this lecture, then it should be this. And I would encourage you to actually program this and like get some experience in this. Okay, what is the entire lecture about? Ultimately, at the core of today's lecture, we're trying to answer the question, where do magic numbers come from? And the reality is, whenever you're dealing with any sort of system, whether it's a computer, a robot, I don't know, anything, any embedded system, a car, there's all sorts of numbers and parameters that you have to type in. You know, like for a robot, you may have to like type in what's the distance at which the robot should stop when a human is in the vicinity. So should the robot should stop like 30 centimeters away from the human, 1 meter, 2 meters, and or where. So that's, you can think of that as a magic number. Like it's some number that you'd have to estimate. There's probably a good number for it, and it's also, there's also ways of choosing bad numbers. So in the case of distances to humans, you don't want the number to be 0 and you're kind of crashing into the human. And so setting parameters is a vital task and a lot of things. And the entire science of determining how we can systematically generate parameters, good parameters, is the science of optimization. Okay, and so let's take a specific example, our specific example that we were talking about yesterday. Yesterday, we were talking about creating a neural network for a robot that would allow the robot to predict whether in the next time step, the robot is going to collide against the wall or not. And then we used that in order to have the robot roam around and not hit any walls. And we were saying yesterday, well, learning in this context is or amounts to determining the weights of the neural network. And basically the weights are numbers that are attached to these connections here. So you see here a neural network with 3 layers. In each layer, we have some neurons. That's those yellow circles there. And the neurons are connected to each other using these connections. And each one of those connections has a weight. And now determining the set of all of the weights for all of the connections is the act of learning here. But another way of thinking about this is really, it's like trying to guess a password effectively. You can think of these parameters. You have like a big string of parameters that you have to set in order for your neural network to do the right thing. And it's like a big password where each element of the password is a number. It's a continuous number. So 0.5, 1.2, and so on. And you have to guess all of these numbers correctly. And so if your network has 10 connections, then the set of numbers, or the size of numbers, is 10. You have 10 numbers you have to set. And that here is determined by the parameter, or defined by parameter d. So in mathematical terms, and by the way, you can forget all of these equations, or not equation, but like these mathematical notations, but I'm writing them for completeness sake. So what we're trying to do is to set a parameter vector, w, which has dimensionality r of d, where d is the number of weights. Just to visualize this again, remember yesterday we were saying that a neural network, or neuron in this case, has a set of inputs, and each one of the inputs gets multiplied by a weight, w1, w2, w3. So if we were to have a neural network that only has a single neuron, this specific neuron here, and we wanted to learn, to do some learning on this, then that would amount to, in this case, setting 3 numbers, W1, W2, and W3. And if you guess the correct 3 numbers, your robot is going to do something correctly. And if you have the wrong 3 numbers, your robot is going to do something badly. And so really, learning is really guessing these numbers, guessing the weights. But of course, I mean, guessing is not a really good idea. So how can we go about that? And that's called optimization. Okay, so one technique to go about this, which is very simple to implement, but also not the smartest out there, is just brute force search. In this case, let's use random search, like random brute force search. And so what that really means is we just randomly generate some W's. So that's what you see here on the x-axis. We generate some W's depicted by these dots there, these black dots. And then for each one of the W's, we run our neural network. We put the W's into the neural network, we run it, and then we see how good was the response of the neural network. That's this f of W. So we evaluate the W, the goodness of the W. In our specific case, we want, so what this f function here does, it's basically what we denoted as the loss yesterday. It should tell us what is the difference between our ground truth data, the data that was provided by the user, or the data that the robot collected in the real world, versus the data that the neural network generated. So the outputs of the neural network compared to the actual measurements that were collected in the real world. What we want to do is to minimize the difference between them. And that's what we called yesterday the mean squared error. So f of W here is the mean squared error. And we want to minimize that error. So ideally, we would choose a W somewhere here, kind of close to this valley over here, or ideally really at the bottom of the valley, so that we minimize the overall error between, or the discrepancy between what we should be getting from the neural network and what we're actually getting from the neural network. So this is just randomly generate some W's, put them in the network, and then see, does it work? No. Okay, let's generate some other ones. And we keep the W's around that have the lowest value. Now, that's of course not really smart. We can do something better than this. And that really is what the backpropagation algorithm that I talked about yesterday is about. What the backpropagation algorithm does is the following. You start at some W, kind of that's the one here on the left. That's where the black dot is. We start there, and rather than just randomly sampling around, we calculate what's called the gradient at that point. The gradient is the direction of steepest descent. Now that may sound a little bit kind of funky, gradient, steepest descent, but really it's just the derivative. You just calculate the derivative and then go down the negative derivative. So not in the direction of derivative, but in the opposite direction of the derivative. So ultimately you take a point on your function and you differentiate it and you go down the derivative. And so that's what you see there. That's the first step that you see there. And that gives you a new point. And then you take that new point and you calculate the gradient at that position again. That gives you a new direction to go. So that gives you a new W. And there you calculate it again. And that you do that again and again until some stopping criterion is reached. And typically people use as a stopping criterion things like the W doesn't change that much anymore. So you're starting to make like minimal to no changes to your weights. So in other words, you start with some random weights, you differentiate with respect to your loss function, and then you go downhill again and again. You kind of iteratively differentiate and go downhill, until you get to the bottom. That's exactly what the backpropagation algorithm is about. And that's what we were talking about yesterday. So all of that is great, but unfortunately, it comes with some assumptions that may not be necessarily true in the real world. So I'm pretty sure in kind of any one of your kind of high school classes, probably on analysis, you've learned that for functions to be differentiable, they need to be continuous. Effectively, they need to be kind of smooth and continuous functions. But many times when you're doing optimization with like real world things, like robots and cars and so on, your loss functions may not be differentiable. They may look like this, like what you see here, like some sort of jagged function. This stuff here is not differentiable at all. Not only that, it may also have, for example, noise in it, which kind of makes things even more awkward. So noise basically means that even when you evaluate the same W twice, you may get two different numbers for it from the function. And so these assumptions that we're making when we're doing gradient descent, they're not necessarily always fulfilled. Well, how can we go about that? Well, there is an entire class of algorithms called hill climbing algorithms. And the idea really is we don't calculate any gradients. We just calculate, or we just sample again randomly. So this is a stochastic optimization technique. So we generate, for example, here, what is it? 5 candidates or 6 candidates of possible positions where the optimum could be. And then we take the best one of those, basically the candidate position that has the lowest error. And then we sample randomly again, close to that one, take the lowest one again, and do this again and again. So rather than calculating a gradient, we just randomly sample around our current hypothesis of where the optimum is. And then we take the lowest value, and then we sample again there, and take the lowest value and sample again, and so on and so on. Okay, so let me just jump over. Actually, no, we can keep this slide. So everything that I explained so far makes the assumption that you have a single hypothetical solution. So a single W that you start out with. Maybe it's random at the beginning, and you start making modifications to it. And there is, however, an entire other class of algorithms for optimization that doesn't have a single hypothesis at the beginning, but it starts with a population of hypotheses. It basically says any one of these 10 possible locations could be the optimum. And let's try to change all of them and try to get closer and closer to where the optimum is. And so these are called population-based methods. So there are some solutions or some methods that use a single solution, they try to optimize it, and others use an entire population, a set of solutions, and then try to improve them. And what I would like to talk about today is one of those population-based methods, which is called evolutionary algorithms. Let me just see if there's anyone asking a question. No question so far. Interesting. And by the way, again, feel free to hammer me with any questions. So an evolutionary algorithm basically imitates biological evolution. And I'm pretty sure kind of all of you have heard about biology and kind of evolution in school or at the university. So it turns out what biology is pretty good at and natural evolution is good at is to create organisms that are adapted to their environment. It's basically an optimization process. So think about, for example, kind of like humans that have evolved from kind of apes, kind of our ancestors were apes, and before that, actually, potentially even like animals in the sea. So we evolved from all of these animals through a process of complexification. And ultimately, humans are highly adapted to their environment. We can manipulate objects, we can walk, we can use tools and so on. All of these skills allow us to really kind of act in our environment and be very to be able to reproduce in the environment. So the most important thing in evolution in the real world is to be able to reproduce and get children. And so some scientists thought, hey, that's actually an optimization process, and we can use or leverage the same principle to solve numerical optimization processes. Basically solve optimization problems in the virtual world. Okay, I'll be going through the details of this, but the most important thing for you to keep in mind is that basically in evolutionary search is like a loop. And within this loop, we repeatedly evaluate the fitness of individuals. We select the fittest individuals. We mutate them a little bit. And we allow them to perform crossover, which is basically sexual reproduction. Basically, the father and mother of an individual generate the offspring. And so through this repeated loop, we can perform an optimization process. Sounds a little bit funky, but it actually works. And so again, all of this builds upon Darwinian evolution. And here's just a picture of just showing how all of us basically started as like really kind of microorganisms, bacteria, and so on, and we evolved over different millennia and hundreds of thousands of years, millions of years actually. We evolved into mammals and kind of then humans. And one thing that's very important, by the way, in all of this is diversity. And so you hear this word being used a lot also in political debates, but it's actually at its core, it has nothing to do with politics. Without diversity, we would not be able to evolve. Our species would go extinct, basically. And kind of diversity is a very critical element of this evolutionary process. So without there being different and diverse set of animals, we would probably be going very quickly extinct due to some disease or to some change in the environmental condition. And so now, how can we leverage all of this? It turns out that people from different countries started thinking about that. So people in the US, some people in Japan, Germany also, and it started somewhere around the 50s, 1950s. Not all of these people worked together, and as a result of that, we ended up with having a set of algorithms. Some algorithms are very close, if not the exact same thing, but just developed at different countries. You know, like some German algorithm and an American algorithm, basically doing the same thing, just being a little bit different. And so as a result of that, we have now kind of a family of algorithms that are called evolutionary algorithms. So evolutionary algorithms is not just a single algorithm, it's really a family of algorithms. So you have things like genetic algorithms, which were developed in the US, evolution strategies were developed in Germany, particle swarm algorithms in the US again, genetic programming, I think, somewhere in Europe again, evolutionary programming, gene regulation networks, artificial immune systems. All of these methods are basically translating this concept of biological evolution, or at least some nature-inspired approach, into a formal optimization process.
Heni, we have a question.
Yep.
Are evolutionary optimization algorithms more expensive computationally?
I would argue no. And in fact, one of the big advantages of evolutionary algorithms is that you can parallelize them very easily. So it's very easy to basically push them on like 8 or 16 cores or something, and potentially also implement them as a shader on your graphics card. And so as a result of that, you can have substantial performance boost by basically parallelizing the algorithm. So I would argue no, like not, like I wouldn't say that they're qualitatively different from other optimization algorithms out there, even though that's sometimes claimed by some other researchers. In fact, like in my opinion and like my experience, evolutionary algorithms are some of the most efficient optimization algorithms out there. There is a caveat to that I will kind of maybe talk about later or maybe not. One of the caveats is that proving that an evolutionary algorithm is going to converge is not easy if, and we don't have like a global convergence proof. So on the theoretical side, there are some, basically they don't come with some of the guarantees that you find with other optimization methods. So if you're a hardcore mathematician, you could tell me, oh, like you don't have a convergence proof. And then, yeah, maybe kind of that's an argument. But when it comes to computational efficiency, they are quite efficient. Okay, or at least they can be quite efficient, and depends on how you implement them. Okay, so let's get back and let's try to use this concept of evolutionary algorithms for optimization. And so let's take this example here. And this example, just for the sake of visualization, our goal is actually not to find the minimum, but to find the maximum, kind of the top of the hill rather than the bottom of the valley. And so we're trying to find the x, which would maximize this function here, f of x equals y. And so the question is, which x should I choose to find the maximum for this function f? And as I mentioned earlier, in the real world, you may have some really challenging functions. So for example, on the left side here, we see multimodal functions that have multiple peaks. You can have functions that are non-differentiable, so like very spiky and stuff. And you can have functions that are basically zero or some number, some constant everywhere, but for a certain location where they have like a spike. And these functions can be needle, they're called needle in the haystack functions. And for those functions, evolutionary algorithms can actually be pretty powerful. And so that's what we're going to do. And now let's take a look at the components of an evolutionary algorithm. We have a population, we have the mutation operation, we have the recombination operation, and the selection operation. And you do them in a loop, you execute them in the loop in order to perform optimization. Okay, so again, we start with the population. We actually, most of the time, people start with fitness first. You evaluate the fitness, and then you do mutation, selection, recombination. But really, the order is not, there isn't a very fixed order. It's just these things, kind of fitness evaluation, mutation, selection, recombination, you have to perform. So let's try this out. For our specific problem here, let's start with a population that has 3 possible solutions. So it's a population with 3 individuals. One individual is minus 0.92. Another individual is 0.76, and another one is 1.33. So that's our population. And now what we do is to assign a fitness to each one of those population members. So what we do for that is we calculate the value of the function for that specific point. So the value for minus 0.92 is somewhere here. That's like 0.15. The value for 0.76 is a little bit higher, so 0.42. And the value for 1.33 is actually something negative. That's pretty bad. And so now what we can do is we can actually, let's do selection first before we get to mutation. So we can select the fittest individuals, and we want to put them into the next generation. So if we go over here, which one of these is the fittest individual, by the way? Anyone help me? What would you say is the fittest individual in this case? Please write into the chat.
Feel free to put it in the chat or raise your hand. Yeah. Yeah,
raise your hand or write into the chat, please. Second one, yeah, 0.76. It's exactly that. Yeah, Pranav and anonymous attendee. Yeah, it's exactly that. So the second one has the highest fitness. And so what we want to do is to select that one and get it into the next generation. So there are different ways of selecting that people have implemented over the years. And one of the most famous ones is actually roulette wheel selection. And it's really kind of cool. I like it a lot, actually. Let me just kind of draw how that would work. Basically, you assign each one of your individuals a pie, like a chunk of a pie, based on their fitness. Yeah, like based on the fitness. So basically, like in our case, we had 3 individuals. One had a bad fitness. We assign it kind of a small chunk. One had a medium fitness. We assign it a slightly larger chunk. And that one in the middle there had a pretty good fitness. We assign it kind of the largest chunk. So now we have a roulette wheel with 3 chunks. And okay, let's say kind of this is here the point at which we read it out. And so what we do is we spin the roulette wheel we spin the roulette wheel 3 times to generate the next population. We spin it 3 times, and every time we spin it, it will land at one of these 3 locations, and then we will choose the individual that kind of where it lands. Basically, let's say, for example, the very first time we spin it, this area A over here for the individual in the middle, that's the one that's going to be here at our marker. And then we say, well, we let the individual in the middle, we let it have a child. And if we spin it again, maybe A actually gets yet another child. And then maybe by pure chance, when you spin it the 3rd time, this area here is actually kind of the small area is at our readout element. And so then we say, actually, in this case, the individual with the lowest fitness gets to replicate and get into the next generation too. In other words, even if your fitness is low, that doesn't necessarily mean you don't get into the next generation. It just means that your chances of getting into the next generation are low. So that's called roulette wheel selection. There is another type of selection, which is tournament selection. You choose 2 individuals, let's say kind of the first one and the one in the middle, and then compare them against each other. Which one has a higher fitness? Okay, the one in the middle has higher fitness, and then you put it into the next generation. And then you again randomly choose to compare them against each other and put one of them into the next generation. Okay, so that's selection. And then let's take a look again at mutation. Mutation is relatively simple. So if you have some individual, in our case, for example, minus 0.92, which was, I think, the first individual, then we can just randomly make a small change to the value. It's a small mutation. And so we change the DNA, we make a small mutation to the DNA. Yeah? And in our case, it basically just means we just randomly add or subtract something from it or to it. And now to recombination. So how can we have 2 parents generate an offspring? Well, in our earlier case, that would be relatively simple. You can just take 2 numbers, so 2 individuals, and then average them out. So calculate the mean of them. So minus 0.92 and 0.76 would generate actually something in the middle here, minus 0.08, which actually would be a pretty good individual to take in. Some people actually prefer to use binary code for their representation. So rather than representing the number as like in a floating point number, they represent it as a binary code. In that case, you can do recombination by saying, if these are the 2 parents, I cut at some location and then swap out the DNA of one parent with the other. So basically we had 0, 1, 0, 1 here. And here we had 0, 1, 1, 0. And then we take the 0 from the lower parent, swap it with the top parent. And so as a result of that, we have 0, 1, 0, 0. And then the lower parent would become 0, 1, 1, 1. Okay, cool. And then ultimately, it's just this evolutionary algorithm loop again and again. We select some parents using the, so actually, first we create a random population. You randomly start out with some random numbers. And then you test the fitness for each one of the individuals. And then you have a while loop in which you repeatedly select the fittest parents. You create P individuals by recombination. So you have them kind of have this reproduction. And then you mutate their children. You kind of add small changes to the DNA of the children. You test the fitness again. And then you increase the generation timer, saying, okay, now we move on to the next generation. And then restart all of this again. So repeatedly select, recombine, mutate, test fitness. Select, recombine, mutate, test fitness. And if you do that again and again, then over time, your population becomes better and better at solving your problem. Okay. So this slide actually may not be very important right now. I may get back to it later on. Let's start immediately with an example. So who knows what the traveling salesman problem is? I've written it here, but just to make sure that I judge the audience right, who has heard of the traveling salesman problem? Yes, no in the chat, please. Yes, no? Come on, people. Tell me, traveling salesman problem. Have you heard of it? Yes or no? Please write it into the chat. No? Meaning I remember hearing about the traveling salesman. I've heard about it, but I kind of forgot what it was. Yeah, it's sometimes you hear about it, but like people don't necessarily kind of think about it often, but it's actually a very important problem in computer science. And the idea is very simple. You're a salesman and you have to go visit a couple of cities as kind of a sales representative, and you need to sell there. So you're given a set of cities that you have to go through, and then at the end you need to come back to your home. So you need to come back to the first city. And the question is, how can you get through all of the cities and minimize the overall distance, or the overall kind of distance traveled? Let's put it this way. So again, the traveling salesman problem describes a salesman who must travel between n cities. The salesman wants to keep both the travel costs as well as the distance he travels as low as possible. And typically distance means travel costs, actually. So for example, here you're seeing kind of 8 cities. And the question is, how should I connect these cities and get back to my original city, city 1, so as to minimize the overall distance traveled? Okay, so, well, let's solve it using evolutionary algorithms. So in our case, in this specific case, we don't have the weights of a neural network that we want to modify. What we have to modify here is the sequence of cities that we have to go through. But it's basically a very similar thing to what we were talking earlier about learning a neural network. It's just that instead of setting the weights of a neural network, now we need to set the number, or like the numbers of the cities in sequence that we're going to travel to. So for example, kind of this first individual that we see here at the top would be a solution or potential solution where we go from city 1 to city 2, and then from there to city 3, then next to city 5, from city 5 to city 4 to 7, 6, 8, and so on. Now, so that would be one individual in our genetic algorithm. And we can, in the beginning, we just randomly generate individuals by randomly generate these sequences of numbers. Okay, so we can randomly generate them. And making a mutation to an individual is relatively simple. You can take 2 cities and swap them out. So that, for example, instead of going from city 2 to city 3, we first go from city 2 to city 8 and then to city 5. And we only get to city 3 at the end. Recombination, in this case, kind of taking 2 individuals and have them have an offspring, basically means to cutting somewhere in the middle and then swapping them out. It's what I showed earlier with the 1-point crossover, kind of a swap out. And fitness in this case is just the length of the path through the city sequence. We want to minimize the length of the path. And so using an evolutionary algorithm, we want to find the best possible path through all of the cities. And so let's take a demo, look at the demo for this, so that you get a better feeling for how this works. Okay, so here we have a set of cities. What's the optimal path through all of them? What's the least, kind of the path with the least distance through all of these? Anyone an idea? Anyone an idea? What should be the path of the of least overall distance traveled going through these cities? Should be pretty obvious though. Anyone? No? Are you afraid? You should not be afraid of me. Do we make some swaps? Yeah, so, so I think some people are kind of still a little bit confused about the 1-point crossover. Let me just explain that quickly. So if this is a sequence, and then here we have like kind of, let's say kind of this is my sequence number 1. So individual number 1, sequence 1, and then sequence 2. What I can do is to just kind of make a cut here, for example, and then swap them out. So for example, I could basically say I go to city 2, 3, 5, 4, and then from there and then I take the second part from the second sequence, and then from there I go to 7, 6, 3. Okay, so in this case, I just kind of took the first part from the first sequence over here, and the second part from the second sequence, and I created a new sequence 3, which is basically the offspring or the child of both of these sequences. Now, well, sequence 3 in this case is actually not a good sequence. It would give us a bad reward because it would visit the city 3 2 times, which is like basically a violation, and so it would get a bad score. So I hope that answers the question of kind of what the one-point crossover is. You basically just make a cut. You take 2 individuals, you make a cut in between, and take the first part from the first one and the second part from the second one. Okay, so, but still, I want to challenge you on this. I'm not going to let this pass like this. So what should be the optimal solution in this case? What's the optimal solution of getting to all of these cities that you see here? Anyone? Come on, help me. It's very easy. I mean, it's what you see. Just someone should communicate with me. No? Okay, I mean, I'm just going to give it away. It's obviously a circle. So ideally, we would go in a circle kind of from one city to another here. And if we do that, then we basically, we optimize the, let's see, oh, yeah, okay. And then optimize the distance. Okay, so let's see if that would work or not. So now I'm going to just press run, and you can see here the evolutionary algorithm really, really quickly. So in the beginning, it actually it starts with some. Can you see it?
No, we can only see your slides.
Oh, you can only see my slides. Oh, sorry.
Yeah.
Oh, that explains a lot.
That's probably why they can't answer. Yeah.
So let's share the entire desktop. I would share the desktop. Oh, okay. So let me just. So sorry about that. I didn't know the desktop was not fully shared. So okay. Let's see. Can you see it now?
Yeah. Would you mind re-explaining what you're doing?
Okay. So now we have these cities here that are on a circle, and we want to find the minimal path, the minimal distance path through all of these cities. And it obviously should be, in this case, a circle. So because otherwise, if we go, for example, from the left to the right, then we incur quite a long distance there. And so the best possible way here to go from some point through all of the other points and back to the original point is basically just to go along the circle and get back. And so what we're going to see here is the optimization process, where this route is automatically found by the evolutionary algorithm. It starts in the beginning with some random routes, and then over time optimizes them. You can see here, by the way, the generation, basically how many times it iterated. And in the beginning, it's just doing random stuff, and then eventually, kind of, it finds the highest, kind of the fittest individual, which is a route that goes through all of the points and back. And we can also see here. So if I make a slightly different a slight modification. So in this case here, we're using tournament selection. So that's why it's called their tourney. It's the thing that I explained with the pie, kind of with the roulette wheel. Oh no, actually, no. So tournament is where you pick 2 and you have them compete against each other. Now we're going to do roulette wheel selection. And let's see if that, I think that's a little bit worse. I think that takes a little bit longer, the roulette wheel selection, for it to find the optimal path. Yeah, it may even get stuck. Uh-oh, it got stuck. And come on. But you certainly see that making good decisions with regard to mutation and recombination is really critical. I actually found the right solution in the end. And so now think about this. If you are working at UPS And you have to maximize or optimize the routes for all of the UPS trucks and UPS drivers and so on. You run exactly such a TSP, traveling salesman problem. But they have to run it on like hundreds of thousands, if not millions of cities and drivers and so on, yeah, all around the globe. And so you can imagine that that's really tricky, but exactly such evolutionary algorithms are used in these domains in order to solve that problem. Okay, so this is one example for an evolutionary algorithm. Let me just kind of actually move on. Let's take another example for an evolutionary algorithm. In this case, we want to optimize the policy of a robot. So let's get to a robot that looks very similar to the robot that we used yesterday. So we have 5 sensors, kind of here. These sensors tell us how far away we are from some obstacles. That's our robot, and this is the goal. And now, let's assume we have an additional sensor that tells us whether the goal is on the right of the robot or on the left of the robot, okay? Now, a policy for this robot, some function that tells us how the robot should move, could look like this. It could be a table that tells us, well, what happens when sensor 1 is active? So when sensor 1 says, oh, there is an obstacle, and the goal is to our left. 1, for example, here, this 1 over here means we have to turn to the right. What happens when sensor 2 is active and the goal is to the left? We're going to turn to the right again. If sensor 3 is active and the goal is to the left, then, well, we turn to the left, and so on and so on. So by filling this matrix here with numbers, we determine the behavior of the robot. That's called the policy. But again, this table with numbers it's basically just a table with magic numbers. We don't know how to set them. Well, again, we can use an evolutionary algorithm that automatically tries to find the optimal numbers. Now, the fitness function in this case could be whether the robot arrives at the goal and whether it collides with obstacles. So another way of saying that would be the fitness would be the distance to the goal, because if the distance to the goal is low, then we have a low number there, and the number of collisions. So in this case, we would actually want to minimize this. Yeah? We want to minimize the distance to the goal and minimize the number of collisions. Okay, so let's take a look at that. And if you have any questions there? No, okay. So let's take a look at that. Let's see. And by the way, this is a program that I programmed like 20 years ago. So it's very old. I think it's exactly 20 years ago that I programmed this. What you see there is a bunch of robots. So all of these are robots that want to get to the goal, which is in the left upper corner there. And in the beginning, in the early trials and the early generations, you can see here the number of generations. In the early generations, this population of robots oftentimes just crashes against the wall and turns red. So basically red means they've collided. Yeah? But sometimes, or eventually, one of them will actually make it to the goal. Oh, there's one of them who made it to the goal. Once that guy makes it to the goal, they get to kind of reproduce. And then over time, they get offspring, children, they get that inherit that behavior. And over time, they get better at the task. Then you can see we have fewer and fewer robots that are colliding against the wall, and more robots that actually make it to the end. Some of them come from the left side here, some of them come from the right side. And in all of these cases, the only thing the evolutionary algorithm is changing is this table with numbers. It's just randomly creating numbers. And if the numbers make the robot get to the goal, it keeps those numbers and makes only small modifications, kind of small mutations and recombinations in the next generation. And so over time, you have this kind of family of robots that get really good at getting to the goal. And by the way, so sometimes I start kind of annoying the robots by, so once I get a bunch of robots that actually manage to get to the goal, I annoy them by putting the goal somewhere else. and then seeing if they can still get there. Some of them get there, others don't get there. And again, over time, they can improve their behavior and become pretty good at getting to that goal too. Okay, so any other questions? Nope, no questions so far. Okay, so how can we bring the human in all of this? So far, we didn't necessarily have a human in this, but actually there is something really cool called interactive evolution that allows you to evolve creatures, evolve robots that are adapted to a human partner. And in this case, we're going to replace the fitness function. So we're going to replace this f of x. We replace that by a human. The human that selects good individuals and bad individuals. And so the good individuals get to reproduce, whereas the bad ones don't get to reproduce and get into the next generation. And so for that, let's make a specific example with a video game. Now, the opponents in a video game, you want them to be smart, but you don't want them to be too smart. They have to be smart in a way that is adaptive to you, to the specific user. So ideally, there's a really nice balance between the user and the opponents. And now the question is, how can you evolve opponents that are just a little bit smarter than you? Okay, well, one way of doing that would be to say, well, again, we can use an evolutionary algorithm. We have a population of opponents for which the policies are randomly generated. So you have like, what is it here? 12 opponents that, oh, not 12, it's like 16 opponents, and all of them, these are like aliens. By the way, the video game is basically like the Space Invaders kind of thing. The aliens come from above, and you have like a rocket with like, what is it called? Like a spaceship with which you can shoot the aliens. And so we have 16 aliens, and then we put them, some of them, into the game and have them basically be shot by the user. Some of them get immediately shot, and so they basically lose their position in the generation. Others survive and make it for a couple of seconds in the video game, and they get then to reproduce and get offspring. So if they survive against the user and the user was not able to kill them or shoot at them, that means they're pretty good, and they get to get children. And so over time, the only ones that remain in the population are those that are pretty good and well adapted to the user. Okay, so let's play that game too. So let me see, aliens, I think it's aliens. Okay, so here I'm going to play the aliens game, and so basically I'm going to kill some of these aliens here, and the ones that remain are going to be the ones that are pretty good. And what they're going to be doing, at least last time I played, after programming this, playing this, so they start hovering at the top of the screen and not coming down, because they know if they come down, then it's going to be easier for me to kill them. And so, no. Okay, and yeah, anyhow, you can see kind of that a lot of the agents now of the aliens are pretty good at evading me. All of those will come down. I'm going to shoot you. Anyhow, and so you can see that using this very simple strategy can create some really engaging games that are not too easy and not too hard, and really intelligent opponents that adapt to your gameplay. So, okay. And now let's use another example for interactive evolution. So another thing we can do is to have the computer automatically generate, and by the way, this is a slightly different application process now, or application task. In this task here, we want to generate images, synthetic images, basically to become a painter without ever having to paint. And the way we're going to do that is by having the computer automatically generate the population of images, and you as the user select the nicest looking ones, and they get to recombine and get children, and you can choose from the children again, and through this iterative process, you get better and better looking images. Okay, and so here are a couple of examples of images that were just automatically generated through this interactive evolutionary process. So something that looks like a car, something that looks like an animal, a butterfly, and so on. And just for you to understand the parentage of this. So maybe in the beginning, we started out with some random image like this black kind of thing here. And then from that, we generated two offspring, one that looks like an eye and another one that doesn't look like an eye. Maybe the user now selected just the eye one and we generated some offspring from that. So we get like these two, they kind of look nice, but also this black one, which also looks nice. Now let's assume the user selected the black one, okay? The user selected the black one and says, well, that's actually kind of nice. And it generates now two pictures. And out of these two pictures, the user selects, mostly goes for the one on the left, which looks a little bit like a clown. Now, some sort of fish or so. And so now when the computer or the evolutionary algorithm adds some mutation to this one, we get something that looks like a skull, which is kind of cool. And something else that again looks like a face, another thing. This looks more like a G or something. Okay, and then again, the user selects the skull and then gets a selection of like slightly modified skulls. And then the user selects some of these and so on and so on. And you end up with different variants of this. And similarly, also here at this stage, the user selected this, this face and then got some more kind of clowny looking faces. Actually, this guy over here looks like Mickey Mouse. Or am I the only one that sees that? That actually kind of looks cool. Over here, Mickey Mouse. Yeah, I'm just going to show a couple of results from this. So it's a very neat process. You don't have to define a fitness function anymore. You just need to click on things that work well or look good in this case. And so through this process, people were able to generate things like a sunset, basically a flipper like dolphin. And this is Homer's X-ray I was talking about yesterday. I really find it super interesting. This automatically came out of this process. And to me, it really looks like Homer Simpson under the X-ray. This one looks like a polar bear. And this one.
Just a question, Heni. Sorry about that.
Oh, yeah, please go ahead. Yeah.
When you say a user selects the generated image, then based on the selection, new ones are being generated on the fly?
Absolutely. Yeah. So you select the image, and then since we have the genetic code of the image, which is the the weights of a neural network, for example. Actually, in this case, each one of the images was generated by the neural network. The neural network takes as an input the XY position of a pixel and generates the color. And so when a user selects an image and says, oh, this looks good, then the evolutionary algorithm can take that picture, the genetic code of that picture, which is the weights of a neural network. It makes a small mutation to the neural network and then generates from the neural network a new image or a new image, and then shows that to the user. It may also generate some more random variations of that neural network. Each one of those gives you a new image. And so then the user goes in again and then selects one of the the best looking images, and then this evolves over time. And if you select two images, they get to recombine, have offspring. And as I said, this is similar to sexual reproduction, where basically the idea is that the new genetic code is a combination of the genetic code of or the DNA of the parents, and you take the weights of two neural networks and you just combine them together. And again, I mean, if you look at the results, they look actually pretty appealing. So this thing here looks like the Teenage Mutant Ninja Turtles to me. Yeah, and finally, we may have found Nemo. So this to me really looks like Nemo from Finding Nemo. Okay, so those were a couple of pictures. Here's another video, really cool video, showing how this evolutionary process could look like on a different task. In this task, we are automating the design of a motor cycle, effectively. And so the genetic code here in this case describes the shape of the polygon between the wheels. And you can see there are different shapes there, and some shapes allow the the resulting motorcycle to drive very far, whereas other shapes basically make it get stuck very quickly. And so through this evolutionary algorithm, we can find better and better shapes that are well adapted to the environment and travel longer and longer distances. Yeah. This one actually looks pretty cool. It's actually pretty cool, generally pretty cool in its behavior. And you can see that the offspring then are looking very similar to each other, because like they're small modifications from something that worked in an earlier generation. So for example, these two here are both offspring probably from the same parents with small differences between them. Okay. Now, of course, you can also apply this to robotics, because ultimately this is a robot learning class. What we do in simulation, we can also do in the real world. And so what you do for that is to generate the individual, have your genetic algorithm run in the computer in some sort of virtual world. And then you download the weights of your neural network on a robot, on a real physical robot, and then measure the fitness of the robot, for example, how far it travels, measure that in the real world, and use that measurement then, the fitness, in order to select the next ones for the next generation and so on. So really going from only doing this in simulation to doing this in the real world only amounts to adding an evaluation of the fitness in the real world rather than doing that in simulation. Here's another really cool one. This is actually an app, like a website. You can see there the website here, Red Nerd Genetic Walkers. So you can try this out by yourself. And it's basically a genetic algorithm running in your browser, evolving the behavior of a human walking and trying to have the human walking longer and longer distances. And one thing that's really cool about this app, or kind of this website, is that you can actually see in the beginning the population, kind of all of the individuals that are generated in a population. The majority of them actually die. You can see all of those blue humans kind of just falling down, because those are mutated and recombined evolutionary neural networks that actually don't allow the humanoid to travel a longer distance. Yeah, so you can try this out in your browser. It's actually kind of cool to watch and really fun. Here's a variant of this. This was presented at a conference about 7-8 years ago. And so they used this again for computer animation and video games. And in this case, they actually also added muscles. And so as a result of that, they can model this dynamic hip-like behavior really nicely, and you get some really nice animations. And so they used an evolutionary algorithm to both change the design, the shape of the animal or the human, as well as the muscle structure and the behavior, how this thing walks. Okay, so let's take a look at this. It's going to take a second until we get there. So really interesting creatures coming out of this. And again, all of this is automatically generated. Okay, now the optimization process, which is an evolutionary algorithm. You can see in the first generation, they pretty much fall over immediately. And then over successive generations of the evolutionary algorithm, you get more and more competent behavior out of it. And so at generation 900, the agent is already pretty good and basically stable. I find the generation 80 one here really funny. You're going to see that it deviates away. It's still walking, but it just deviates away slightly to the right there. It just goes off until it falls down. Kind of funny. Whereas the generation, what was it, 900 or whatever, was actually pretty good. And this brings me back to the original video that I showed you at the beginning of my lecture of a robot learning how to stand up by learning from a human, but then optimizing that and changing that automatically. And well, that's again an evolutionary algorithm, or actually something, not exactly an evolutionary algorithm, but a small modification thereof. And yeah, we were able to have the robot learn and autonomously adapt and change its behavior. And over time, it was then able to stand up. And more recently, we use this kind of stuff to teach a robot how to locomote on sand. And in this case, it's actually poppy seeds. And so programming this little robot was actually kind of arduous. And so by using these kinds of evolutionary algorithms, we were able to have the robot travel longer distances, and it was less of a pain to program it. And actually, now that I'm thinking about it, Alper here, kind of our boss, you could say, he actually also implemented an evolutionary algorithm in one of his projects where he taught a robot leg to walk on the ground. So he taught a legged robot how to walk, which is also pretty cool. And so with that, I come to the end of this lecture series. I hope I was able to give you kind of a hint of the basic concepts of machine learning and robotics. In particular, we were talking about neural networks and evolutionary algorithms for optimization, but all of that in the context of robotics, like how can we solve challenging tasks for robotics, and how can we make the first steps in this field using these techniques. Yesterday, we were talking about PyTorch, and PyTorch implements a lot of these techniques: neural networks, optimization, gradient descent, backpropagation, evolutionary algorithms. So I would recommend to you that you try it out yourself. If you have any questions, feel free to reach out to me, and I'm more than happy to take any additional questions or discuss whatever you are interested in for the next 15 minutes or however long it takes. So yeah, thank you all so much.
Thank you so much for being here with us today and for all three of your lecture series. We have one question in the Q&A. If anyone else has a question, feel free to ask ahead. Someone asked, are there any software frameworks that you could recommend to explore interactive evolutionary algorithms like image generation and offer options to see the evolution of the neural network weights for the generated images?
So actually, that's a great question. There used to be one, but I'm not sure kind of it's actually there anymore. Kind of Pick Breeder was one. It was called, oh, now it's called Art Breeder. So it's actually a website where you can do that. Actually, do you see my screen?
Yeah, we can see it right now. Yeah.
So basically, you can start, and I think it also comes with code. Oh no, it kind of needs an account. Okay, whatever. Kind of we can log in kind of with one of my accounts. I'll just do that. I probably gave away my life right now. So yeah, kind of you choose pictures. So let's see. Let's start kind of with something else. Yeah, let's take something here a little bit more kind of environmental. That's kind of cool. Okay, so let's take kind of, I take that picture, and now out of that, I get like these variations as a result. So these are the offspring, and there are still some things you can change about this. And well, in our case, kind of, I'm not going to play around with those sliders. I'm going to say, well, I'm going to take that guy, and so on and so on. And you can also add your own genes, by the way. Can I say that? Let's crossbreed. And actually, let's do children. Let's just do children. So when you click on children, normally some children should appear. That actually kind of looks good. So all of these look kind of nice. I think the one in the middle I like the most. So you take that, and then once you have that, I think you can. Actually, let's make it a little bit more different. Yeah, and you can save those. Kind of, you can save the images, and then over time you can also crossbreed it with something else. With something, I don't know, crossbreed it with that guy. Yeah, you get some weird stuff as a result, but it's still cool. It's still fun to see. Yeah, what kind of results you get for crossbreeding, like one image versus another. So anyhow, this is called Art Breeder. It used to be called Pick Breeder, and it's a nice way to get into it and still have some fun. I hope that answers partly at least the question. So thank you so much for the very kind words there. Truly appreciated. Yeah, and feel free, everyone, to reach out to me if you have any additional questions, or if you just have a specific question, for example, regarding your project. Really, and I said that in the beginning, the most important thing for me is to get you excited about this this entire field and get you started. It's not hard. It's not hard at all. Just get started. Do your own project. Alper can tell you stories. He's done multiple projects on robotics and machine learning, evolutionary algorithms with me. Right now, he's doing one on virtual reality. So just get started. That's the most important thing. Don't think like there's anything that should hold you back. So I hope you are excited. And if there's anything I can help with, reach out to me.
Thank you so much again, Dr. Ben Amor, for being here with us.
Thank you so much. And well, in that case, I would like to thank you again, especially Alper, for really accommodating me and kind of also helping me out throughout the administrative days and kind of through that side. Thank you all for attending, and have a great weekend. And again, kind of let's stay in contact. If there's anything I can help with, reach out to me.
Yeah, if you guys need his LinkedIn or anything, Dr. Ben Amor, I don't know if you want to share your email, but depending on that answer, feel free to DM me on Slack. My name's Alper. So yeah, just feel free to ask me.
Alper, can you add my email address, or just my ASU email address, if
Sure.
you can add it to,
yeah, sure.
Absolutely.
Yeah, definitely.
Everyone should be able to.
Definitely. Great.
Thank you so much, and have a great weekend.
Thank you. Have a
Bye-bye,
great
everyone.
weekend, everyone. Bye.
Thank you. Bye.